Now that we've learned about cells and their organelles and the things that they do, we're going to learn about how chemical reactions relate to how cells are able to live. So this next topic is chemical reactions and the laws of thermodynamics. A quick review of what energy is. Energy comes in many forms. You have thermal energy, which is like heat, nuclear energy, mechanical energy, which includes kinetic and potential energy. Mechanical energy is the energy of anything moving or having the potential to move. So the wind blowing the leaves off the tree is an example of mechanical energy. You have electromagnetic energy and chemical energy. Chemical energy is where we're going to spend most of our time, because living organisms use chemical energy to perform life functions such as active transport and mitosis. One of the questions on your assignment is to list these two things that living organisms use energy for, and then to come up with two more of your own. Energy changes form, but it is never completely lost. So these things here, they change form from one to the other continuously, but the total amount of energy that we have on this planet is always the same. There are two types of chemical reactions that one would find in a living organism or anywhere else. The first is exergonic. This is a chemical reaction that releases energy because the bonds between molecules are broken. Remember, we talked about macromolecules like carbohydrates, lipids, proteins, and nucleic acids. Everything is made of molecules. If you break the atoms of the molecules apart, it releases energy. Most of the time, this kind of reaction occurs spontaneously, but sometimes it requires a small amount of energy to get it started. For example, in a living organism, breaking down food molecules during digestion is an exergonic reaction. And these types of reactions most often produce heat. So if you've ever noticed that after you've eaten a big meal, your body starts to warm up a little bit, it's because of the exergonic reaction that's occurring as you digest your food. Endergonic reactions are the other type of chemical reaction. This is the opposite of exergonic. Endergonic are when bonds between molecules are formed, or atoms are brought together and joined in a bond. This requires quite a bit of energy to happen. The energy that is required is called activation energy. And these type of chemical reactions actually absorb heat when the reaction occurs, so it feels colder than its original state. These do not occur spontaneously, but only when there is energy available. And many cellular reactions are endergonic, therefore cells must have a way to store the energy they need for use in these chemical reactions. Just a quick note on theories versus laws, because we're going to start talking about the laws of thermodynamics. So let's review what a theory is. A theory is an explanation of a set of related observations or events based upon proven hypotheses. A hypothesis, remember, goes with a particular experiment. Theories are more like laws than they are hypotheses. A theory is much more complex than one hypothesis. It has to be verified multiple times by detached groups of researchers. And one scientist cannot create a theory by him or herself. They can only create a hypothesis about a particular, random thought that they have, and then those hypotheses kind of get combined to become a theory. For example, theory of evolution, the theory of relativity, and the quantum theory. A law, on the other hand, is a statement of fact meant to explain, in concise terms, an action or set of actions. These are generally accepted to be true and universal by all of the scientific community, so there's no debate about a law. A law is accepted to be true by everyone in the scientific community because it's never seen to be untrue. It can sometimes be expressed in terms of a single mathematical equation, so laws can sometimes come back down to math. When X, Y, or Z occurs, it always comes out this way when it's been measured. They're accepted at face value based upon the fact that they have always been observed to be true. For example, the law of gravity, Newton's laws of motion, and what we are going to study, the laws of thermodynamics. So theories are a little more complex, a little more vague, but they are more closely related to laws than they are to hypotheses. A theory and a law are similar things. A law has never been seen to be untrue. It's explaining something that is always occurs the same way under the same conditions. So on to the laws of thermodynamics. Thermodynamics is the study of energy, and the term dynamic means to change. So in reality, it's the study of how energy changes. The first law is called the law of conservation of energy. To conserve means to keep or to hold. And this law states that energy is always conserved. It's always been kept. It's not created. Energy is not created nor destroyed. It is simply changed from one form to another. Remember the forms at the beginning of the presentation. We had thermal and nuclear and electromagnetic and chemical and whatever the last one was that I forget. Here's an example of how energy can change. If you have a stretched rubber band, when it's stretched out and being held there, that has potential energy. When the rubber band snaps, all of that potential energy turns into kinetic energy. The energy does not get destroyed, it simply changed forms. The total amount of energy in the system is the same. In short, the quantity of energy always stays the same. The second law is called the law of entropy. This states that even though the total amount of energy does not change in a system, the form of the energy will increasingly go from usable energy, like chemical energy, to less usable forms, like heat. Heat is not a very usable, or thermal energy is not a very usable form of energy. You can use it to do things, you can use it to move turbines and things like that, but it's not a very efficient way. This going from usable to unusable forms is called increasing entropy. Entropy is the amount of disorder or chaos in a system, and as long as there's a continuous energy transfer, entropy remains very low. The higher the entropy gets, the more disorder there is. In relation to biology, the second law says that energy in living organisms is used for growth, repair, motion, cell division, things like that. But if this energy is constantly used up for these things without any input of more energy, the organism will die. So in short, the second law relates to us because if we don't continuously take in food, which is chemical energy, break it down, and then use that broken down form of energy to allow the chemical reactions inside our cells to occur, then we die. And then in short, or very quickly, the third law, which we are not going to work much with, states that if all the molecules in the universe stopped moving, a state called absolute zero would occur. All molecules are always moving. They have this inherent motion to them that isn't stoppable. But if all the molecules did stop moving, this would happen when all the matter and energy happens to be randomly distributed throughout the universe, which means it's at its highest entropy or its highest disorder. And this would equal a negative 273.15 degrees Celsius, which would be absolute zero.